formulas and from the manufacturer's catalog. Now, while we are going to select the CAD belt from the manufacturer's catalog, at that time we are going to have these all steps which may get involved in the selection of belt. Now, step by step, we'll see how to go for the selection of that clad belt. Out of that, first step is that finding pulley diameters. That is the very basic step which is involved in the selection of this flat belt drive. Rather than we'll say it as a flat belt. So when we are going to select these flat belts for a particular application for transmitting the power, at that time, first of all, we are going to find what will be the diameter of that pulley. Now, this step involves finding the diameters of the driving and driven pulleys of the belt drive. That is nothing but the drive which you are going to select, the belt which you are going to select. Already we have decided that the belt drive we are going to use. In some problems, diameter of the driven and driving pulleys may be given. That is, some problem statements are there in which this diameter of the pulleys are mentioned, or where you are going to basically when we are going to solve problems related to the exam, in that statement sometimes problem involves this diameter of pulleys and sometimes it is not going to involve. But where in actual practice, if you are going to work and if you are going to select the flat belt, at that time sometimes you have to calculate, you have to find out the diameter of that pulleys, and that is depend upon the speed ratio or velocity ratio, it is called as. What it means? It means that n1 divided by n2 is d2 divided by, d divided by small d. Now this n1 and n2, these are nothing but the speeds of that driver and driven pulleys in RPM, whereas this capital D and small d are the diameter of bigger pulley and smaller pulley. That capital D we are going to use for the bigger pulley, whereas the small d you are going to use for the smaller pulley. That has mentioned here. That is nothing but n1 is the speed of driving pulley in RPM, n2 is the speed of driven pulley in RPM, then D, capital D, is the diameter of larger, that is driven pulley, okay, and small d is the diameter of smaller pulley, that is driven pulley, okay. So this is driving pulley. So normally already I have mentioned you that in case of this belt drive, 99% the small pulley is work as a driving and bigger pulley is working as a driven pulley, okay. So this driving and driven pulley, that is nothing but the pulleys which you are going to use on motor as well as on the application where we are going to use that pulley. As far as this step is concerned, I think we are not having any doubt because we know this velocity ratio as well as the nomenclature which has mentioned in this slide. If you have any doubt, you can free to us. Otherwise, we will move to the next step. Please. Hello? 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 Can you hear me? Rohit?
Yes.
Okay. Do you have any doubt or we'll move to the next step? This is a very simple step.
No doubt, sir.
Yes?
No doubt, sir. You can proceed further.
Okay, we can proceed further because step by step, each of us we have to understand what that mean. Okay. Now this is very simple step. From this step, when we are going to move to the next step, That is okay. So when we have calculated this velocity ratio, then we are going to select the pulley's diameter from the standard diameters which are available. Okay, that is after finding the pulley diameters, we must to change it to the nearest standard value. Once we are going to get the value from this driving and driver for the diameter of this driver and driven pulleys from the velocity ratio, then we have to go for the selecting of that pulleys from the standard values which are available. Okay. Now these values where we are going to select. For example, I am going to take, if suppose from that velocity ratio we got that diameter of pulley, okay, that is smaller pulley is suppose we got as a 35.6 millimeter, and for the bigger pulley we got that diameter as a 95.8 millimeter. Then we cannot use that values as it is. We are not going to use, actually. We cannot, means either you have to go for the manufacturing of that pulley, or we have to select pulleys from the market having the standard diameters. So while we are going to select that pulley diameter from the standard diameters which are available, then at that time we are not going to select less diameter pulley than the value which we are going to get. Suppose smaller pulley we are going to get as a 35.6 millimeter. Then the nearest value for that 35.6 millimeter is 40 millimeter. So we have to select this 40 millimeter diameter pulley, and the nearest value for the bigger diameter pulley is 100 millimeter, as we are going to get the value as 95.8 millimeter. Then we cannot go for 90 millimeter. We have to go for the further, that is bigger diameter pulley. We cannot go for the smaller diameter pulley. That is the rule of what we can say design. That means it is not mentioned anywhere, but we are going to have the bigger diameter. We are going to find select the bigger values of the dimensions, right? So from this chart, we are going to select the diameter of that pulley. Okay. Once you select that diameter of that pulley, then we can go further. Now all these dimensions are mentioned in millimeter only. Okay. So at the time of examination, these type of charts will be provided to you in question paper only, or it will be supplied later on while the solving that problem. So we don't have to worry about this values. We don't have to by heart these values. This chart will be provided to you while solving the problem. Now, if you are going to use the design data book, then here it has been mentioned that on which page number you will find this data. Okay. Likewise, all the charts or graphs or tables which are mentioned in this design data book. This is a standard design data book, PSG design data book, which normally referred by all the engineers in India. So every time it is not necessary to mention that which page number and where you will find this data, but all this data you will find in PSG design data book. Okay. Also, if you want, you can find this table and data in Bhandari's book as well as Sigle's book under the unit of selection of belts. Okay. So next, we have to go for the second step. Once you find the diameter of that pulley, that is driving and driven pulleys, then again we have to find the speed of that driver and driven pulleys. Okay. So the driving, you can ask question that, sir, already as we have calculated the velocity ratio, then why it is necessary to go again for the calculating of that speeds? No doubt, this you are right. But as the first step has mentioned, that we are not going to take exact value of the pulley diameters. What we are going to do is that we are going to select from the available standard values of the diameter. So when we are going to select that pulley from the available data, at that time, the value which we get will not be matching to the previous value which we are knowing. So when we are going to get the different diameter pulleys, at that time, definitely that velocity ratio will get changed slightly. And to cope up with that slight change in velocity ratio, again, we have to find out new speeds for the driving and driven pulleys. Okay. In many problems, the step of driving and driven pulley will be given. That is the speeds of the driver and driven pulleys are given. Okay. That is standard values which you are going to say. But if the speed is not given, then we have to go for this step. And if it is given also, then we have to cope up with the new or changed value of velocity ratio. Sometimes in the problem statement, only velocity ratio is mentioned. They are not going to provide us data of driver pulley speed or driven pulley speed. Also, they are not going to provide data for the diameters of that pulleys. But if it is provided, then well and good, we can go and proceed further. In that case, it is not necessary to go for this first and second step. Okay? But while solving every problem, we have to go step by step. Getting? That is nothing but first of all, we have to find out the velocity ratio. Then we have to find out the diameters of that driver and driven pulleys. Then while we are going to find the diameter, we have to select it from the standard values. Once you select it from the standard values, then what we have to do? We have to check whether the velocity ratio has get changed. And if it is get changed, then calculate the values of speed of driver pulley and speed of driven pulley. Okay. Now, when we are not going to have the data for the driver and driven pulleys, then in that case, the velocity ratio is calculated, or we can have the reverse calculation from the velocity ratio. Okay. At that time, we are going to we can calculate this velocity ratio in terms of slip of driver pulley and driven pulley. Okay. What it means, let us understand. This means that in some problem statement, percentage of slip is given, okay, for each pulley. And this percentage of slip is directly used to calculate the velocity ratio. Suppose in some problem statement, speed of driven pulley is given and speed of driver pulley is given. Okay, then directly we can calculate this velocity ratio, that is n1 by n2 is equal to velocity ratio. But in some problems where the this n1 and n2 is not given, also diameter of driver pulley and driven pulley is not given. Only suppose they have mentioned what will be the velocity ratio. In that case, from that velocity ratio, just by using the previous formulae, that is this formulae, we are going to calculate diameter of driven pulley and driver pulley. Okay. And if we are going to calculate the diameter of driven and driver pulley, we are going to select it from the standard values. Once you select it from the standard values, then if they have mentioned the percentage slip, okay, that means if you are going to take directly ratio of driven pulley to the driver pulley, that is capital D divided by small d, and if you are going to get some value, that is 10 suppose, but if the percentage slip is given for the driver pulley is 10 and percentage slip which is given for the driven pulley as a suppose again 10, then in that case, due to this slip, this capital D divided by small d value will not be exactly equal to the velocity ratio, because velocity is change in speed, change in distance with respect to time, right? That is the speed. And while we are going to see this change in displacement or distance traveled, at that time the slip gets occur. That means the travel which has done by the pulley is not exactly the travel which has done by the belt because of the slip. In that case, how to calculate the velocity ratio? That velocity ratio can be calculated by means of this N1, that is speed of driver pulley, divided by speed of driven pulley. Okay, N1 by N2 is equal to diameter of the bigger pulley, that is driven pulley, divided by diameter of driving pulley, that is small d, okay, smaller diameter, into 1 minus S1, where S1 is the percentage slip between driving pulley and belt, and S2 is the percentage slip between driven pulley and belt, divided by 100. Of this formula, we are going to convert that percentage slip into exact slip, is equal to the velocity ratio. Now here, I want to just know that whether you have got this point or should I elaborate it once again. Hello? Can anybody of you please respond?
Yes, sir, understood.
You understood it. Okay. Anybody else who has not got this point? For them, I'll repeat it. बऱ्याचदा प्रॉब्लेम स्टेटमेंटमध्ये आपल्याला व्हेलॉसिटी रेशो दिलेला असतो, फक्त व्हेलॉसिटी रेशो, आणि त्या प्रॉब्लेम स्टेटमेंटमध्ये पर्सेंटेज स्लिप मेन्शन केलेले असते, म्हणजे पर्सेंटेज स्लिप फॉर द ड्रायव्हर पुली आणि पर्सेंटेज स्लिप फॉर द ड्रिव्हन पुली. त्या केसमध्ये जरी आपण डायमीटर ऑफ बिगर पुली आणि डायमीटर ऑफ स्मॉलर पुली फाइंड केला, ओके, नंतर आपण दिलेल्या चार्ट मधनं त्याचा तो जो नियरेस्ट असेल तो सिलेक्ट केला, त्यानंतर त्याचा रेशो घेतला तर तो एक्झॅक्ट व्हेलॉसिटी रेशो झाला. पण तो व्हेलॉसिटी रेशो स्लिप मुळे मेंटेन केला जात नाही. मग व्हेलॉसिटी रेशो कॅल्क्युलेट कसा करायचा, तर त्याच्यासाठी हा फॉर्म्युला दिलाय. तो व्हेलॉसिटी रेशो कॅल्क्युलेट करताना आपल्याला एकतर डायमीटर ऑफ बिगर पुली आणि डायमीटर ऑफ स्मॉलर पुली जरी माहित असलं, त्याच्यावरून आपण व्हेलॉसिटी रेशो कॅल्क्युलेट करू शकतो. जर स्पीडच डायरेक्ट माहित असेल, म्हणजे तुम्ही टॅकोमीटर घेतलं आणि ड्रिव्हन पुलीचं स्पीड मेजर केलं आणि ड्रायव्हर पुलीचं स्पीड मेजर केलं आणि त्याचा रेशो घेतला, तर त्याच्यामध्ये स्लिप इन्व्हॉल्व असणार आहे. कारण ड्रिव्हन पुली ज्यावेळेला तुम्ही 200 RPM न फिरते आणि ड्रायव्हिंग पुली ही समजा जर 500 RPM न किंवा 1000 RPM न फिरते, तर डायरेक्टली ह्याचा रेशो घेतला तर तो व्हेलॉसिटी रेशो झाला. कारण ड्रायव्हर पुली 1000 RPM न फिरते, ड्रिव्हन पुली 200 RPM न फिरते, म्हणजे त्याच्यामध्ये बेल्टची स्लिप इन्व्हॉल्व होऊन जो काय आपल्याला स्पीड मिळतोय तो त्याच्यात इन्व्हॉल्व झाला. पण डायरेक्ट फक्त डायमीटरवरनं जर आपण व्हेलॉसिटी रेशो कॅल्क्युलेट करायला गेलो आणि त्याच्यामध्ये जर स्लिप असेल तर तो आपल्याला एक्झॅक्ट उत्तर देत नाही. मग त्यासाठी आपण काय करतो की हे जे स्लिप आहे ती स्लिप कॅल्क्युलेट करतो, त्या स्लिपला आपण कन्सिडर करतो. ती स्लिप कन्सिडर करण्यासाठी हा फॉर्म्युला आहे. तो काय आहे, diameter of bigger pulley divided by diameter of smaller pulley into bracket 1 minus म्हणजे काय की हा जो diameter of bigger pulley आणि diameter of smaller pulley हा झाला व्हेलॉसिटी रेशो, ज्याची व्हॅल्यू तुम्ही एकदा ते पुली सिलेक्ट केल्या की ते पुली तुटेपर्यंत चेंज होणार नाही. पण स्लिप चेंज झाली की त्याच्यामध्ये चेंजेस होणार, म्हणून ते 1 म्हणजे आपण 1 घेतला, त्यातनं सबस्ट्रॅक्ट होणार जी स्लिप असेल ती. ओके, मग किती स्लिप आहे ती S1 प्लस S2. त्याच्यामध्ये S1 आहे स्लिप, ती पण पर्सेंटेज मध्ये मेन्शन केलेली. जर डायरेक्ट दिली असेल स्लिप इज 0.01, देन वी नीड नॉट टू टेक डिवाइड बाय 100. बट नॉर्मली स्लिप इज मेन्शन इन पर्सेंटेज, पर्सेंटेज मध्ये स्लिप दिलेली असते. तर त्या पर्सेंटेजचं एक्झॅक्ट व्हॅल्यू मध्ये कन्वर्ट करण्यासाठी म्हणून आपण डिवाइड बाय 100 करतोय. आणि ती जी एक्झॅक्ट व्हॅल्यू आहे जी स्लिपची दोन्ही साईडच्या म्हणजे ड्रायव्हरची आणि ड्रिव्हनची, ती आपण 1 मधनं सबस्ट्रॅक्ट करतो. राहिलेली जी काही व्हॅल्यू आली असेल तो मल्टिप्लायबल जर आपलं डी कॅपिटल डी डिवाइडेड बाय स्मॉल डी केलं तर त्याच्याशी मल्टिप्लाय केली की आपल्याला व्हेलॉसिटी रेशो मिळतो. ओके. Anybody else do you have any question? Can we move further?
Sir.
Huh?
Yes,
If yes,
sir.
then we are going to go further. This is again micro level thinking. What is this micro level thinking? That you can say, sir, diameter actually of driven pulley is capital D and driver pulley is small d. But what happens if we are going to select a belt having thickness measurable or considerable thickness of that belt? Then whether that pulley diameter is going to be exact diameter? No. What we have to do? We have to take that thickness also into account of that belt. If you are going to same formula is modified, if this same formula is modified when we are going to take into account the thickness of that belt. So what we are going to do is that we are going to consider that the pulley. Let me draw here the diagram with which will be, suppose this is pulley, and on which, if suppose we are going to put the belt. Suppose this white one is indicating as a pulley. Okay, and the remaining, that pink one is indicating the thickness of that belt. Okay, in that case, if you are going to consider only diameter of this white circle, that is pulley, then will not be sufficient. If you are going to consider the thickness also, then this formula will get modified. Here we are going to mention, or you are going to consider thickness of this belt also. Okay, so if you are going to consider this thickness, then just this diameters will be get modified, that will be added, okay, by means of thickness T, where T is the thickness of belt, and remaining formula will remain same, that is percentage slip in driving pulley as a S1, percentage slip in driven pulley as a S2. Okay, and we are going to get the value of velocity ratio. Got it? Hello? Now we'll go further. In step number 3, once we are over this step number 1 and 2, which are quite easy, which you are knowing, then we have to go for the third step. And in this third step, we are going to calculate the power rating of that belt drive. That is nothing but how much kilowatt power you want to transmit by means of that belt drive. Now in problem statement, it may be mentioned that we are going to use 2 kilowatt motor for the driving purpose of any application. Okay, but that 2 kilowatt exactly will not be taken for the design for the selection of belt. That has modified, because you know that when we are going to calculate any stress level also, at that time we are not going to take that stress as it is for the calculation. We are going to calculate the design stress by considering factor of safety. Okay. Likewise, here also that power is not taking as it is for the selection of belt. It has modified by some factors. Now, what are that factors? That factors are load correction factor, then arc of contact factor, then smaller pulley diameter factor. Now, what it means? Load correction factor means what? If suppose we are going to consider that the application where we are going to use the belt drive is of 2 kilowatt, but we know that always that power requirement will not be maintained as a 2 kilowatt. If the load get increased, the power requirement get increased. So it get fluctuate. It may become 2.2 kilowatt or it may become 1.98 kilowatt. So exactly that 2 kilowatt is not maintained. And so that we are going to say that the load correction factor, and that is depend upon where you are going to apply this belt drive. That is depend upon the application of the belt drive. So that load correction factor is taken from the application of that belt. Next, arc of contact factor. Now, these all things we are going to see in details. Okay, but arc of contact means that belt is in contact with the pulleys, and we know that the smaller and bigger pulley will not have the same arc of contact. But all the calculation which we are going to do, we are going to do by considering the arc of contact as the same. Suppose these are the two pulleys, and we are going to have this belt drive. Right. So in this case, this arc of contact, that arc of contact for the smaller pulley will be the point from where that belt is in contact with the pulley. From here, I'll change the color of this. From here to here. Whereas for this bigger pulley, for the bigger pulley it will be higher, for the smaller pulley it will be small. Right. So this is the contact arc, and for the bigger pulley it will be from here to this point. Are you getting my point? Yes. So this will be the arc of contact for the bigger pulley, and this will be the arc of contact for the smaller pulley. Now these arc of contacts are not exactly 180 degree. For the smaller pulley, it is smaller than 180 degree, whereas for the bigger pulley, it is higher than 180 degree. That's why, as all the calculation we are going to do based on 180 degree lap angle, that is the contact angle, okay, arc of contact. That's why we are going to have some corrections, and from that corrections, we are going to take that factor. Likewise, for the smaller pulley diameter factor, that is nothing but the pulley minimum diameter of pulley which is available is 40 millimeter that we have seen in the standard values of the pulley diameter. We have seen, see here is the 40 millimeter diameter pulley is available. So we cannot go below that. If we want to go below that, then it will become special application, and special belt has to be designed for that. But in the standard belt drives, this pulley diameter, minimum pulley diameter is 40 millimeter. So in our application, it may be vary according to the requirement. That's why smaller pulley diameter factor is used. We'll see one by one all these factors. But design power will be equal to rated power, that is power which has been given in the problem statement, multiplied by load correction factor divided by arc of contact factor multiplied by smaller pulley diameter factor. This formula you have to by heart. Okay. And from that, we are going to calculate this design power. Now, how to select that load correction factor? Now, this load correction factor that is mentioned in the above formula here, load correction factor. Already I have told you that it is depend upon where that belt is used. For example, this type of load, okay, when we are going to consider as a normal load, okay, what the normal load is, when maximum load is known. What is the maximum load which is coming? If suppose we are designing that belt drive for 2.2 kilowatt, and that will be the maximum, above which we know that load will not vary, or there is no any possibility of increasing that load above that load. It may get decreased, but it will not get increased above 2.2 kilowatt. Then we can use this correction factor as a 1, as it is that rated power can be used as a design power. But we are not sure about it, like for the steady load. Now, in case of this steady load, which applications are coming? Like light duty fans which are used for the industrial purpose, centrifugal pumps, the pumps which we are using for lifting of water from well or from river, these centrifugal pumps are mainly in the industry of the centrifugal pump, like in process industry or what we call chemical industries. Okay, in that case, centrifugal pump is used. Then printing machinery, that is the application where belts are used. In textile machineries. Okay, then screens, agitators, evaporators, and light machineries. Now in this light machinery, the lathe machine which we are using, that also comes in light machinery. Okay, because bed length is limited in case of the lathe machine which you are using in our college. So that is also coming in the light machinery. So for all these, this power factor or load correction factor is taken as a 1.2. Now you may ask that, sir, where we can get these all values? No doubt at the time of examination, this table will be provided to you. Okay, so just you have to check in which type of application that problem statement comes. In problem statement, it will be mentioned that we have to select a flat belt drive for rotating of pulley of centrifugal pump, and motor power is this and all that. Okay, likewise in problem statement they are going to mention that what is the use where that drive has to be used. So you easily, and this table will be available with you, so easily you can take this load correction factor. Now next is intermediate load. That means rather than the small loads or light loads, we are going to have some higher load, that is heavy machine tools. This heavy machine tool includes the turretlets, okay, big turretlets, then heavy duty fans and blowers. This heavy duty fans and blowers includes the FD fan, forced draft fan, then ID fan, induced draft fan of boilers. Okay, these fans includes heavy duty. Okay, then air conditioners, compressors. So in case of big air compressors, we are not talking about the air compressors which are used in small applications like service station, or where you are going to make the puncture of our two-wheeler or four-wheeler. That are the small air compressors. But in case of big air compressors, then reciprocating pumps, centrifugal pumps are coming in light duty, whereas the reciprocating pumps are coming in the intermediate load duty. Okay. Then elevators, like in mall, you may be knowing that elevators. Then mill machineries, all type of mills. Okay. Then line shafts. Line shafts means the shafts on which number of machineries are used. Okay. Then paper mill and sawmill. Sawmill is also one of the application where belt drive is used. You might have come across that small sawmill. Okay. So these are considered as the intermediate loads. And for that, we are going to use this power load correction factor as a 1.3. Next, shock loads, where the loads are going to vary. And these are more complicated. You know that because in case of fluctuating load, it requires huge assumptions. And we have to go, that will be not the normal design. We have to consider many more factors than the normal design that are called as the shock loads. So shock loads involves the hammers which are used in forging industries, then grinders, crushing machinery, then digitators, vacuum pumps, rolling mills, tube mills. Tube mills means where we are going to have the seamless tubes which are manufactured, seamless pipes. Okay. Then ball mill, then automated machineries, and stamp press. These are some of the applications where we are going to get this shock load. That is nothing but the load. We are not having the surety of changing of that load. Load may get changed as per the time. And in that case, this factor which you are going to use is as a 1.5. Okay. So this is about the load correction factor. Any doubt about it? Can we go further? Once we got this load correction factor from this formula, then we are going to move to the arc correction factor. Now this arc correction factor, as already I have told you, that all calculations, standard calculations are done by considering the lap angle or that contact angle as a 180 degree. But it is not same for the driver pulley and driven pulley. So what we are going to do is that we are going to consider this arc of contact. Okay. And that we are going to correct. And how it is corrected? By means of this arc of contact. First of all, we are going to calculate this arc of contact is equal to 180 degree minus capital D minus small d divided by C, where C is the center distance between two pulleys that we know. Sometimes first of all we have to calculate it and later on we can use it. Or in problem statement, approximate center distance between the two pulleys or two shafts are given. From that we can select this center distance and multiply by 60 degree. Okay, this 60 degree is the standard value which is selected. Okay, now this 180 degree minus 60 degree, actually we are going to consider that exactly if it is not 180 degree, then it is varying by means of 60 degree, but it is not exactly 60 degree. That's why we are going to use this diameters, that is bigger diameter and smaller diameter, as well as the center distance, because angle of lap or angle of contact is depend upon all these parameters, that is diameter of bigger pulley, diameter of smaller pulley, and center distance, as we can see in this diagram. If the center distance gets changed, this angle of lap, angle of contact will get changed. Whereas if the diameter is also going to change, this angle will get changed. And that is accounted in this formula. Got it? Now, once you got this arc of contact, then depending upon this arc of contact factor is mentioned in this table. Now, if suppose we are going to get this arc of contact value as a 110 degrees, then it is not mentioned in the table. What we can do? We have to go to the nearest higher value. That is 110 degree. Instead of that, we are going to consider this 120 degree. And for that, we are going to select the factor. That is 1.33. Likewise, you have to calculate the arc of contact from the formulae, this formulae. Okay. And by means of this table, we have to select that factor. No doubt, once again, I'm going to tell you that this table will be provided to you at the time of problem solving in examination also. The next is how we can select the smaller pulley diameter factor. Now, the smaller pulley diameter factors or the standard pulley diameters are given in the table, this table. So you can consider the smaller pulley diameter in millimeter. Up to 100 millimeter, we can have this factor as a 0.5. From 100 to 200 millimeter, it is 0.6. From 200 to 300 millimeter, it is 0.7. From 300 to 400, 0.8. 400 to 750, it is 0.9. And above that, it is 1. Okay. So this table will be provided to you at the time of problem solving. And by means of that, we can overcome this step number 3. That is, you can calculate the design power. Okay. Now, before moving to the next step, step number 4, let me know if you have any query or question or the part which you have not understood. Hello? If not, we'll stop here today. So before we are going to stop, let me know, do you have any query? Anybody of you? Pratik Deshmukh.
Hello. Yes, sir.
Do you have any query?
No, sir.
No, that's good. Anybody else? Athar Kulkarni.
Yes, sir.
Have problem?
No, sir.
Okay, you understood it?
Yes, sir.
Good. Omkar Pawar.
Yes, sir.
Yes, any problem?
No, sir.
No, good. Then we'll stop here.